When it comes to checking for a normal distribution, we have four key things that we need to carry out. So the first one is to look at the distribution around the mean and including the medians and things like that. The second one is looking at the concepts of skew, either to positive or negative, and kurtosis, which looks at the height of the distribution in a curve. The third one, we have a battery of tests, and the one we're going to look at today is the Shapiro-Wilk test, which is a normality test. And the last one is to plot the residuals against an actual theoretical distribution called a quantile plot, or a QQ plot. And we're going to have a look at how we do that in Jamovi. So I've got some very simple data. I've got two treatments, 1 and 2, and I've got the counts for those treatments, and that's our outcome variable. We're actually going to just use the count data here. Jamovi already has the capacity to look at the residuals, so we don't have to calculate the residuals before we do the normality test, because these normality tests are already testing the difference between the individual values and the mean of that entire sample. Now, in some textbooks it tells you to look at the residuals based on the individual treatments, but general consensus is if we look at the whole set of data and we look at the residuals against the whole sample mean, that is a perfectly appropriate way to look at our normality. Anyway, so let's look at our first check. So the first check is like all the other ones in our descriptive stats. So if in the analysis menu, we're going to go to exploration, we're going to go to descriptives, and everything we're going to talk about we can find here. We're just going to put in the count in the variables. We're not going to put the treatment in the split by. So we're just looking at the count, and here we've got our basics. We've got a mean and a median that are exactly the same, so it looks like this could be a normal distribution already. But let's make some further analysis. I'm just going to minimize statistics for now. We're going to start off with looking at a histogram of the data. It's always good to eyeball your data first, and here we've got the histogram that shows a frequency distribution of the different values, and we can see that actually we've got a few outliers at the higher end. So that here is we're showing a positive skew of the data. It's not where the peak is, it's where the long tail is. So if you just imagine that curve, see it's just extending that tail out. So that might be a cause for concern. Those values are pulling the distribution away from that nice even bell-shaped curve that we like. So that's our histogram. The other ones we're going to look at are in the statistics section. So let's have a look there. So on second of the tests, we're going to look at skewness, which what we just talked about. And here, so I put a tick in skewness, and it gives us a value in here of 1.57, and a standard error of the skewness of 0.46. That's important because actually, if we want to do a very precise measurement of whether skewness is telling us that this is normally distributed or not, we take the skewness and divide it by the standard error. And if that value is less than 1.96, or between minus 1.96 and positive 1.96, because this could be a negative value, then it would be normally distributed. If it's outside those values, so beyond negative 1.96 or above positive 1.96, then we have causes to think that this is not a normal distribution. If we just treat that as about a half, if we divide something by half, we're actually multiplying by 2. That gives us a skewness overall value of over 3, well over our limit of 1.96, and therefore we think this is a skewed distribution, which is against our normality idea. If we look at kurtosis, which is looking at the height of the curve as opposed to that skewness, it's the same. We look at the value divided by the standard error, same 1.96 figure, and again it's well over that threshold. So we don't think this is normally distributed because of these two values. But a test that is specific for a normality is a Shapiro-Wilk test. There's other tests available. There's Kolmogorov-Smirnov test, there's a Anderson-Darling test, there's a number of tests of normality, but Shapiro-Wilk is a very standard one in our animal and biological sciences. So let's put a tick in that box. And our Shapiro-Wilk test gives us a p-value of 0.002. So the null hypothesis here is that the data in this data set is normally distributed, or there is no significance and the significant difference between these data and a normal distribution. And the probability of that statement being true, remember a p-value is the probability of a null hypothesis, is 0.002 or 0.2%. So the chances of this being or the probability of this being a normal distribution is 0.2%. So alternatively, it's 99.8% likely, I say very likely, to not be normal. Oh, well, that means that our tests based on a parametric assumption are not necessarily going to be valid. A final check is the quantile plot. So here's a QQ plot here. So this plots the current data, or the residuals of the current data, against a theoretical normal distribution. If I put a tick there, nothing seems to happen. We have to scroll down and find it. Here, the straight line is the theoretical normal distribution, and the dots are our data. And you can see that this sort of bend, S-bend, is generally, the more bendy this is, the less likely it is to be a normal distribution. So that is a concern for us, and it's particularly driven by these two outliers here. When we look at an assessment of normal distributions, we've got four separate things there, and what we actually do is we look at a battery of evidence. We look at the range of evidence here. We look at those four checks, and although those four tend to coordinate, they tend to be coherent with each other, that's not always the case. So if we're looking at the four checks and perhaps the skewness and kurtosis is okay, but this QQ plot is well out, it's generally these plots of the histogram and the QQ plot, or the quantile plots, that are actually quite informative, and we should be concerned that our parametric tests are not necessarily going to deliver. Remember, we've got parametric tests that can deal with departures from normality as well, so we're less worried about that. But we can do something about it, and that's the transformation of data. So I'm going to go back to the top here. Let's go back to our data. So we go to the data, we've got our columns, we've got the treatment column and the count column. If I click on the count column, I'm now going to transform the data into a format that might be better. Now you might think that's the transform menu, but that's for recoding columns. Actually what we want is the compute button. So I click compute, and I'm going to rename this one log of the count, because we're going to do a logarithmic transformation. You don't really need to know just too much about what a logarithm means, but I'm sure you can follow that up. But we're going to use a natural log, or that's base E log, and doesn't matter. What we're going to do is transform these numbers into a distribution that does look like a normal distribution. So here we're going to put the log count, and we're going to use this functions wizard here. So we're going to put in the function, and we're going to natural log is this one. We've got the natural logarithm of a number. We've got a log to base 10, which you often see as well, but we're going to go for this logarithm of number. We'd have to double click on this side first to bring in the ln and the brackets, and then there's cursors within the brackets, so we're going to do the natural log of count. So we're going to double click count, and then we're going to press this button here, and it will populate this column over here. Boom, there we go. So we've got a range of numbers that have derived from our original data that we can possibly use in further analysis. So let's get rid of that by pressing this up arrow here. And now I could do all that again, but if I could simplify that by, if I go back to my old analysis, there's the descriptive results for count. If I click on that box, the table, it brings me back to the analysis I did here. So I can go to the this top box, and where I had count before, I can add the log count underneath it, and it's carried out all the same maths for that. So if I look here at my skewness, you can see that the skewness of the new data is really reduced. Standard error of the skewness has stayed the same, but that is no longer an issue. Kurtosis has dropped from 3 to 0.73, so that is much more within the normality. Standard error is staying the same. The Shapiro-Wilk test p-value was 0.002. It's now 0.21, well above our 0.05 significance threshold. So we are not significantly different from a normal distribution. That's the plot, the histogram from the original data, and that's the quantile plot from the original data. Underneath now we have a new histogram which is much more even in its distribution to support that lack of skewness significance. And here you can see the dots are much more likely to fall along that straight line. We still have these two outliers. We'd probably be concerned about them and make sure that they're actual data, not errors. But here we can see much more even distribution along this straight line of a theoretical normal distribution. Okay. So there's no perfect way to check normality, but there are 4 tests, and we look at the range of evidence available to us and we make an informed decision based on that. Thank you for watching.